So let's get started.
Yes,
My presentation about the database of asteroids for the purpose of space mining commission analysis. And this work is done at ECOCEL in Toulouse, in France, in the laboratory called Space Advanced Concept Laboratory. So the presentation is organized as follows. First, I'll introduce the project we work on. Then I'll talk about the structure of the database and the tools which we developed to create and to work with the database. And to conclude, I'll give our future steps. So this work is part of the project called ECOCEL. ECOCEL means from French exploitation of resources of celestial bodies. This is an interdisciplinary study which includes various aspects such as legal aspect, engineering aspect, economics, geography, and political aspect for political aspect of the mining of space resources. And the goal of the ECOCEL project is to prepare recommendations and an overview about the space resources for the French government to provide it in order to define a strategy of France in the industry of space mining. And from our side at Space Advanced Concept Laboratory, we are responsible on the aspect of engineering aspect of the space mining. And we lead study on resources and their accessibility from Earth on technology and time frame for possible space mining missions. So now I'll present the database which we developed to analyze the resources of asteroids. The selection of best targets for resources can be proceeded by two directions, by two components. The first is the composition of asteroids. This includes valuable resources. It can be valuable metals for economical resources, or it can be raw materials to use in space, such as water, for instance, to use for the propellant. Or it can also be scientific samples as resources to study to provide any information about the evolution of the solar system from these primary bodies as asteroids. Another important factor of selection of best targets is the accessibility from the Earth, which can be measured, usually is measured in the time of flight or in delta V for the space mission. And this can be estimated from a simplified mission analysis, which I'll introduce later. So to create the database, first we collected all available data in already existing databases. Then we completed this data by composition of asteroid, and then we added information about mission opportunities to the selected objects. So now I'll talk in more details about each step. So first we selected all near-Earth asteroids from the JPL Small-Body Database. The near-Earth asteroids as the most accessible from the Earth. And then we selected only objects which have a defined spectral classification Here they are Tholen or SMAS2 spectral classification. And we got, as a result, 326 objects from this database, where we also collected all information about orbital parameters and physical parameters such as an estimated diameter. And then we completed the database by composition data. For this purpose, we used established link from literature. The links about the information available about meteorite samples on Earth and the spectral types of asteroids. We could complete the database by an estimated chemical composition of asteroids, and also we included water and all these listed chemical elements. It should be noticed, however, what this composition is only an estimated composition related to the surface, and obviously internal structure and composition is not defined. And we included in the database the fraction of each element. And on the third step, we added information about mission opportunities. So we computed one-way missions around the Earth asteroid. This is a rendezvous mission analysis, and also for round-trip missions with a stay on asteroid and return to the Earth. For this purpose, we developed tools which are included in the framework of the SEMPy package. The SEMPy, it's a Python package which is under development at JPL, and it is aimed at mission design and analysis in the Sun-Earth Moon dynamics. Now I'll give more details about these tools of the SEMPy package we developed. So for the mission analysis to analyze missions to asteroids, we use ephemerides provided by space kernels from a JPL Horizon system to get the position and velocity of the Earth and asteroids. Then we apply Lambert solver. So we use a simplified two-body model to compute an optimal conic trajectory between 2 points and given the time of flight. Then we used the two-body approximation and Pachaconic approximation to compute maneuver if specified parking orbit around Earth. And in this case, the delta V is the sum of this maneuver from the parking orbit and the maneuver to match the velocity of the asteroid at arrival and then to departure from the asteroid. And for any object in the database, the SEMPy tool allows to make an analysis given mission constraints such as launch interval, the total mission duration, and stay at an asteroid if it's a round-trip mission. To compute the delta V and time of flight and other mission parameters for any object. So here is a demo of the the use of the SEMPy tool to analyze mission opportunities. So as inputs, as I just said, we give constraints like launch interval, mission duration, stay on asteroid, and departure park in orbit if it's specified. And then as a result, we can get an optimal solution. And here the optimization can be done by various parameters. So it can be optimized by the time of flight, the total delta V, or specifically by only inbound or onboard path of the round trip mission, or by a hyperbolic axis velocity with respect to the Earth at arrival or departure, or to the asteroid. Now next, the tools which we developed to work with the database. To work with the data and the code we developed in SEMPy, we use the Jupyter Notebook interface. This environment allows us to use the models written on Python, which are already in the SEMPy package, and also to use the data which we already collected about the selected asteroids, and the pre-computed trajectories, which we also included in the database. It is an open source and flexible for development of new functions and for new data. So all of the functionalities are described in the SEMPy documentation. I cannot give all these functions. I just give the basic options of these tools. So the first main functionality is to make a multi-criteria target selection, since it was the goal of this database to make a selection by both criteria, by composition and by the accessibility. So the selection can be done by initial parameters such as time of flight or delta V, or in addition by composition, for instance, for specific chemical elements or water, or by any parameter for any parameter such as orbital parameters or physical parameters like diameter, which we collected from the JPL Small-Body Database. It also allows, the SEMPy package also allows to show the pre-computed one-way and round-trip missions, pre-computed solutions for all asteroids in the database, and to see the properties of these pre-computed trajectories. It also includes a few visualization tools, for instance, visualization of the composition of an asteroid or a set of asteroids. And now to sum up, so we compared our database with other existing tools, which are NASA Ames tool, JPL mission design tool, and Center of Near Earth Objects. So we validated also our results using results from these databases. Our database contains less objects, obviously, because we selected only objects which have a defined spectral type. Now we pre-computed now we have pre-computed trajectories for the launch interval between 2020 and 2050, but it can be extended. And also the mission duration now is specified for 450 days for one way and 900 days for a return mission. We didn't specify a delta V limit. We collect all solutions in the database, and we didn't include yet flyby possibilities to compute the optimal trajectories, but the database already includes both one-way and round-trip missions, and the park in orbit around the Earth can be specified. And the most important difference from all these existing tools is that our database contains composition data, which is not included in other databases. So it allows us to perform at the same time selection by both criteria, accessibility and compositional data. Now, for our future steps, we are planning to develop tools of SEMPy, for instance, by adding tools to compute possibilities of lunar flyby or multi-target missions. And we are planning to perform a data analysis because we haven't done it yet, to make an interpretation and visualization of the all data we collected and computed, and make a statistical analysis based on this data. And at the end, this overview and of the possible emissions for space mining to asteroids will be included in the final report, which contains different aspects of space mining and will be provided to the French government. Now that's all. Thank you for your attention, and if you have any questions.
Okay, thank you, Irina.